Hello, so this is going to be my presentation of Lab 5 E104 SJSU. This is going to be the Heartbeat project. So let me share my screen. So as we see here, this is the heart rate signal peak detection. This is going to be the heart rate signal that we have here. The beats per minute are 115.80, and the rejected peaks are shown in the red dot, or the orange dot rather. And here we have the code. So import HeartPy as HP. So this is the HeartPy library within Python that we have to import. Import pandas as PD. So that's another Python library that we downloaded. Import matplot .pyplot. So that's the Python library that allows us to plot different signals. It's similar to MATLAB where you plot things on MATLAB, but it's the Python library for it. It's basically the matplotlib library. So our sample rate is going to be 250. So 250 is basically our sampling rate for the heart rate signal peak detection. And this line right here, df is equal to pd.read underscore CSV, PDA output underscore mono2.csv. That lets us to load the CSV file. A CSV file is basically an Excel file. So that lets us to load it and check the columns of print df.column. So this prints the columns within Python and selects the correct signal column. So data is equal to df m values. That lets us select the columns that we want within the Excel sheet. So let me pull up the Excel sheet. So this is the Excel sheet that we can download for the heartbeat. Um, this Excel sheet is basically founded from the heartbeat website, which is right here. And I chose patent ductus arteriosus. It's basically a heart defect where one of the valves that doesn't close properly. So you download the MP3 here, and from the MP3 you have to convert it to a .wav file. And then from .wav, you basically can use the Python library script to convert that into a CSV. And so when you do that, you do get this CSV output right here. And when you do that, you basically also get these values that are in 128, 120, 120. This is a mono signal. It's mono, so that's why you get the same values. But in order for Python to be read, as stated right here, the CSV has to be normalized to the .xxx format. So it has to be basically divided by 1,000 to be converted into a decimal value. So that converted value is shown right here, 0.128, 128, 128. So that's right here. And that is the data that we're importing into the Python library script. So that is what we basically loading over here. So from that Excel sheet, when we say data is equal to dfm, we're basically loading the values from the column M. So which is shown right here. So this is column M, and then these are the values from that column, and those are the values that you load onto the Python. So once we select that data, we are replacing M with the correct column name. So let's say that if the column name was different, then we can just replace it with a different column name. So plot the raw data. So plt.figure fig size 12.4. That's basically setting the plot standard for it, setting the plot axis and everything. Then plt plot.data. This is the command that lets us to actually plot the data. And then we have plt.title raw heart signal. So that sets the title. So the raw heart signal is basically right here. So as you can see, this is the raw heart signal for the plot. And plt.title raw heart signal is what we just mentioned. And then plt.show, that basically lets us to show the heart signal. So this is the raw heart signal right here. And when we run the analysis, WD, M is equal to HB.process data sample rate. So we're sampling the rate, we're processing the sample rate that we obtained. And then we're going to visualize that process data. That's shown in line 32, 33, and 34. So 32 lets us visualize it. So plt.figure fig size. So that's all such that we could plot this signal right here, the heart rate signal peak detection values. So this plot comes from that line of code. And then we print out the computed measures. So for measuring M keys, print F, measure M, and measure 0.2F. So 0.2F is again signaling the floating value, the float precision that we want for 0.2F, and that is shown right here on the heart rate signal peak detection. So each of these values are at 0.2F. And that's also why we have imported the Excel sheet when we converted the M values to divide by 1,000. That's why we had to do that. So we could print it in 0.2F precision. So that has been the heart rate signal peak detection for EE 104 Lab 5. Thank you so much. Have a great day.